So I think we can start if Professor Resch Bernd is ready. First of all, we are very happy to have you here. So we can start.
Good morning, everybody, or close to lunchtime for you guys. So my name is Bernd Resch. I'm a professor for geosocial artificial intelligence at ITU in Linz in Austria. ITU, Interdisciplinary Transformation University, is a newly founded university that has just started. So we're building up from scratch, so to say. And the idea is to have a public university that tries to build a totally different university model. So, for example, we solely focus on project-based learning, and that's the only, so to say, type of courses we have. And we start from the problem and then work our ways backwards, so to say, towards a solution and the required skills that need to be learned as well. Good. So what I would like to talk about today is multimodal analysis of geosocial media data for improved disaster management. Why that is, I'm just going to say in a second. And the subtitle here is, you say, from science to digital practice. I'm also going to show that this is not only a research or scientific endeavor, but it also goes into practice already. Good. So where do we start from? That's the world we live in at the moment, right? On the bottom top left, you basically see this Maslow pyramid of basic human needs, where you say, okay, the further down you are, the more essential it gets. So the physiological needs are the ones that you really need, like, I don't know, water and food and a roof above your head and so on. And then you can care about safety and security, your friends and so on. And then up on top, self-actualization. You do what you always wanted to do in your life. And now there is this caricature that basically says it has been extended towards the bottom part, meaning if you're not connected to the internet, yeah, we get a little bit nervous these days. And then if the battery is dying, I mean, there are some existential questions that we need to ask ourselves anyway. And there's a bit of course, a caricature way of thinking about this. But then when we think about it, it's realizing also that we're quite dependent on our digital tools, obviously. Now, the benefit for research is that we have these, let's say, very large-scale data sources, which could come from social media, but also from mobile phones, from wearables, which is like this quantified self-movement and so on. And these data are very diverse in nature. So as you see here, like on the bottom right, we have textual data, we have videos, we have images, we have timestamps, we have geographic locations, which is always important. And we have a number of other modalities. And trying to make sense of this is just a very good way of gaining insight into various different situations in our world, including natural disasters. Now, of course, that's not so easy, especially when we do NLP, natural language processing. Text that is expressed in social media is usually not adhering to grammatical and standard rules. So it's more a big mixture of, let's say, non-formalized expressions. So the second motivation why we do this and why TAMA, the project, was set up as well, is that disaster management to some degree is still a very much, let's say, analog process. So what people do in a crisis situation, and that's not a very old picture, it's still happening like this, is that they print out a gigantic map, I don't know, 2 by 3 meters, pin it to the wall, and then they start drawing borders on that, drawing flooding areas, having post-its and writing on there, then having these small focus maps and all different kinds of things. But then again, obviously, this kind of situation does not foster up-to-dateness of information, interinstitutional exchange of crisis information, reliability and up-to-dateness and topicality of this data and information, and so on. So obviously, we think that through, first of all, big data analysis, but also through digital tools, we can improve this process. Social media and crisis management. By the way, when I'm talking about social media, I'm always meaning geosocial media. And this means our social media posts, each and every one, have a geographic reference inherently attached to them. This means that, for example, when people post on Twitter, X, Instagram, Facebook, whatever it is, they attach their current position, for example, as measured by their GNSS or GPS device, to the post. So we know where people have posted from, which is absolutely essential for our research, as you will see. Good. Now, why do we think that using social media data analysis in disaster management is important? Now, back in one of our previous projects, the European Commission asked us to basically implement and research a system that uses crowdsourced data, which is social media data, to analyze a disaster situation and get hold of what's happening there. Why? Current previous approaches, which are mostly based on remote sensing data, basically suffer from a number of shortcomings. For example, a temporal lag. So until the image from a satellite is downloaded, until it's processed, until the information is ready, a few hours or even days may pass. Limited resolution, spatially and temporally, obviously. And then lacking information for change detection, like this pre-post analysis, so to say, is always a challenging situation there. And that's why we decided to go for this social media-based system. Of course, there is a number of uncertainties and research problems that need to be tackled. Some of them I mentioned before with respect to NLP and language expressions. But there is also, of course, a problem with timestamps, like with texts. We often don't know whether people refer to a past, present, or future event, or whether they refer to an in situ location, so they report about what's happening right next to them, or whether they report about remote locations. So all this needs to be tackled, obviously, but I'm just going to show how we do this and what the outcomes are. Good, so generally speaking, social media give us fast, it's real time basically, right? Geolocated, very important as I mentioned before, and then multimedia information. What you see here is from the 2021 Central European floods. It's a real post, right, from Instagram, where we basically have a description of what's happening. It even says where, it's a city in Austria. There is a picture and actually a video attached to that. It gives us a very quick insight into what's happening on site there. Now that's a very similar one from Germany in this case during the same event. Now you see that there is a lot more text already. You see also that the text is multilingual, in this case German, but also other languages obviously. There is a more detailed description of the situation. From the image you see pretty much instantly what's happening. And then of course this can happen as well, that people even attach maps to their own posts, or very clear damage images or statements as well. And that obviously gives us a very quick insight into what's happening on site. And I mean, of course, we're not analyzing individual posts, like from our point of view, but we're downloading like masses of posts, trying to make sense of them, and then convey the resulting information to disaster managers. Good, so that's a very general workflow that is not always happening exactly in this way, but this is at least one possibility. Just to say quickly, we start from raw data and we want to go towards a insight situation that we can then judge and convey towards disaster managers. Pre-processing, of course, always a very important idea. You know that like data science is mostly data engineering. And this also means pre-processing, really trying to make this data, the raw data, processable. And we have a number of 14 or so different pre-processing steps so that the data are actually processable by a machine learning system. Good. Then for us, semantic topic modeling is usually a way of pre-filtering. So we have a large mass of data, and if we only signal into a certain topic that we want to see, for example, a natural disaster, then we get a very clear signature, so to say, temporal signature, but also a spatial signature. Yes, of course, accuracy assessment, but then again, the spatial hotspot analysis is the thing that makes our research a little bit more unique, meaning we do not only have time series of a disaster, but we know in quite a fine-grained fashion what happens where in these disaster and damage footprints. So let's take a look quickly at the temporal view. This is a 2-week time series of a disaster event, an earthquake in this case in California in the US. And you see that these are very characteristic patterns, like the daily patterns here. People post until close to midnight, 11 in the evening, for example. Then it drops off. There is a small dip during lunch break. And that's very much reproducible, by the way, for very different kinds of user-generated data sources, including mobile phone data. And then people post a little bit less here on the weekends as compared to during weekdays. Good. Now we have this like very clearly identifiable pattern. It's very constant, and there are no big surprises, except for what happens here. We see a very strong anomaly, and if we zoom into that's on the next slide. That's exactly that. So in orange, we see a normal Sunday, which is basically from 0, like from midnight to 6 in the morning. People don't post very much. On the y-axis, we have the number of tweets per minute. Number of posts goes down close to 0. Actually, everybody's sleeping, and then after 6, things start rising again. Good. Now, 1 week later, what happens is in blue here that we have exactly the same curve, basically, and then all of a sudden this 90-degree angle occurs. Like what happens, obviously, the earthquake occurred, and now you can make a guess when it occurred. It occurred exactly at 3:20:21. So there is a 0-minute delay when people are shaken out of their beds, like in a 6.2 earthquake. The first thing they do is grab their phones and tweet on the internet, like how everything's shaking, that they experienced an earthquake, that there are damages and so on. Now that's the, let's say, nice phenomenon for us in the sense that we can use it in research through big data analysis. Now that's the temporal view. And the next one is the spatial view. And that's always the specificity, again, of our research, right? Now, the algorithm that I showed before now says, in red, we have areas that are affected by the natural disaster. In this case, the earthquake. And in blue, we have areas that have not been affected. In yellow, we're not so sure. We're just talking about statistical probabilities here, right? If you see here is confidence intervals. But in the end, this conclusion can be drawn. Now, if we compare this with official data, in this case from the USGS, US Geological Survey, with the earthquake footprint, which is really like measuring using seismographs how strongly the earth was shaking. So percent of PGA means peak ground acceleration, how strongly the earth was moving. And what we can see is that, of course, these red areas are overlapping very strongly with the green area, which is the earthquake footprint, and then also the borders between blue and red, where it can be felt. For example, here between San Rafael and San Francisco, or Concord and Oakland, or Napa and Sacramento, are very well delineated. We can say, and that's the general storyline behind here, that social media are a pretty good window into the world, so to say. Even though we're not there on site, we know what's happening there pretty nicely. Good, of course, this is transferable to a number of other use cases. In this case, flooding after a hurricane. What you see here, same methodology, is that basically Houston is flooded after the hurricane and San Antonio and Austin are not. Now, if we overlay this with a flood map as derived from remote sensing imagery, we see that there is a bit of a mismatch. First of all, and that was obvious before already in the first earthquake map, the social media hotspots are mostly present in densely populated areas. In other words, where nobody posts on the internet or on social media, we're basically blind and we don't see much. On the contrary, remote sensing data are very good over large areas, as you see here in green, which is flooded areas as derived by the Dartmouth Flood Observatory. But now then what's striking is that in here, in the middle of Houston, the remote sensing information does not show any flooding. Good, if we take a look at the situation on site, that's what it was. And you see that, for example, here the trash bins are like a meter underwater. Now, why is that happening? Probably you know. You see that in the background, you see these like densely built up areas. And the problem with remotely sensed imagery is that, of course, you don't always have a nadir, like a 90-degree angle of recording your information, but there is some kind of tilt usually as well, right? And this means according to shadowing, to multipath effects, and just to lacking visibility of the ground, you just have not such a great view of what happens on the ground using satellite imagery. And that's where the two sources basically complement each other. Again, remotely sensed imagery, very good in large areas, social media data, very good in densely populated areas. This is like at least a few excerpts from what we convey really to disaster managers during disasters in somewhat real time. First of all, of course, these timelines, like how intense the situation is, then this map of posts, and you see already, this is a few days during the Central European floodings, and these clusters show that there are a lot and lots of relevant posts that we see in the area. And this is only, by the way, posts that are relevant to this specific disaster. So 3,000 here in this cluster, 300, 650, and so on, 1,300. A lot of posts. All in all, it's about 4,000 to 5,000. And now, of course, what you can do is, this is an interactive map. You can zoom in there. And if you zoom in, you can click on each of the posts. And for example, here it says, okay, this river is high and causes flooding. You see this in this bridge here, and it's flooded plus the image. So when you click there, you get a very good view of what's happening on site there. Good. So this is the temporal, spatio-temporal view. Basically, we see those hotspots occurring, disappearing, moving from A to B over time. And sometimes they're a bit more constant, as you just saw here in the R region. And sometimes they're a bit more volatile and they're jumping around, so to say. And this gives us, on different spatial levels, again here, a very good view of like what happens where and when. So first, everything's yellow, not too much happening, but all of a sudden, those hotspots appear. And that's a very good early warning capability that disaster managers can use to deploy their resources and to define regions which need special attention. So what we showed right now is basically a sequential workflow of single steps that does pre-processing, semantic analysis, spatio-temporal analysis, and so on, right? Now, what the problem with sequential workflows is that they disregard the multimodal nature of the data themselves. So sequential workflows are oftentimes not able to capture an integrated phenomenon that is defined through information in multiple modalities. And that's exactly where we go in here, also in TEMA. We're researching a workflow that basically takes textual data, semantic data, the geolocation and the time, and then of course a few others that I'm going to show. It fuses it into a multimodal model, and like this produces interpretable, let's see, multimodal clusters of these posts. Now, how does that work in more detail? Over here, you see the input document. Latitude, longitude, text, and timestamp. Latitude, longitude go into coordinates. So we need to do projection and scaling. The text goes into two different modalities. First of all, semantics. So we do semantic topic modeling, just as I showed before. We identify topics that people talk about. Then, second textual analysis part is sentiment and emotion analysis. How do people feel? Because there is a very different quality when people talk about disasters and they say, oh, we're just cleaning up and yes, it's horrible, but we're looking, let's say, positively towards the future, and thanks everybody for helping. Whereas I had to flee on my roof and I need very urgent rescue. A very different quality, so to say, in what people express on social media. And that's why the sentiments and emotions are a very, very important part. And then, of course, the time. I mean, time and geographic coordinates are just the very important and basic context features that we always need. So we put those into feature vectors and then do some kind of clustering. In this case, it's a self-growing geosum, a self-organizing map. Basically, what it does is a dimensionality reduction methodology that has BMUs, best matching units, that are defined in n-dimensional space. And then each post would represent a point in this n-dimensional space according to these feature vectors that we have defined. And what it then does is that it assigns each post in n-dimensional space to a best matching unit. And if there is a very, let's say, large amount of posts closely around a best matching unit, this we would consider a homogeneous cluster. And this is exactly what we're looking for. Good. The great thing is this supports multiple languages, so we have no problem with multiple languages in our data set, which is always a challenge in NLP. And the output there is a cluster with clear topic, sentiment, location, and time, as I'm going to show in a second. It's basically a map that contains multiple information pieces. Before we do this, just going quickly into how the semantic topic modeling works. In this case, we use BERT, which is a state-of-the-art transformer-based module. And what it does is it groups posts that talk about which words define a certain topic when we talk about, I don't know, let's say damages and so on. And the second part is topic document, like which topics, semantic topics that people talk about are present in which document. And we can use this to interpret what people are talking about. It's quite homogeneous. Now, this interpretation is always subjective, obviously. And these captions here have been generated using Llama, this or methods generative AI model for semantic text in this case. So this is not done by ourselves, but done by a generative model. Good. What the output look like? That's one of the outputs we generate. What you see here is, first of all, a number of clusters that are somewhat homogeneous. And remember, these clusters are defined by geographic location, by time, by the semantic topic, people talk about the same thing, and the sentiment. Now, you see that we see yellow and red clusters, that's the sentiment as by the legend here. Neutral sentiment in yellow, red, negative sentiment in red. And then you also see the size of the clusters, right? Also spatially speaking, but also in terms of these clustered areas, like hotspot areas, so to say. And then you see what people talk about. Again, weather, disasters and everyday struggles, flood, infection and health, devastating floods in Germany-Alpha region. Okay, so you see that people are desperately in need for help. And then down here, flood disaster and government criticism. This is more like criticizing the government for not taking action, for not protecting people and so on. So it's a very different quality of what people talk about, and as a consequence, what they need from humanitarian aid organizations. So this was the disaster case, and what I'd just like to show is that this approach can be transferred to a number of crisis situations in different application domains. First of all, epidemiology. This here is a time series, which is very similar to the one I showed before. Right here, and only during the rise, halfway through, the WHO declares a pandemic. And that's a very interesting phenomenon. And this is proven like for all different kinds of phenomena, including flooding, including earthquakes, including wildfires, and so on. Good. Now, what's interesting here, what I'd like to point you to is this figure on the bottom left. Namely, we see the blue curve that we just saw before as well. That's the curve of COVID-19 related social media posts, in this case, tweets. And the orange curve here is the curve of daily new confirmed cases of COVID-19 in the US. And what we see is that the curve, like from a temporal signal analysis viewpoint, behaves pretty much the same way. Namely, quite strong rise, and then it flattens out. Quite strong rise, and that's it. Just because, and that's the clue here, we have a 14 to 17 day gap here in between. And this represents exactly what I said before. The social media curve is actually ahead of the epidemiological curve. And that's a very interesting fact. Now, if we take this to the spatial viewpoint as well, we can take a look at this. Again, in this case, hotspots show hotspots of COVID-19 occurrence as derived from social media data. And what you can see is that at some point, these hotspots get more stable here in the northern part of New York State. Cold spots appear, and this gives us a very good and fine-grained idea of what's happening in the real world. So where corona hotspots are and where they will be. And that's the point here. They work with pharmaceutical companies, and they tell us, look, what we want to know is where the next hotspot will be in like 2 to 3 weeks. Because what we want to do is we test our newly developed vaccines, and we know which testing center. They have like 30 testing sites throughout the US, which test center we can use, because we need the people to be exposed to the virus in order to prove the efficacy of our vaccine. And then I would like to go into another use case, which is humanitarian safety in this case. Again, more or less the same thing. The motivation is a little bit different, obviously, and it's a very strong humanitarian crisis that we're facing. These are images from the city of Salzburg at the border between Austria and Germany. This is at the train station where these field beds were built up. And this was directly at the border, basically at the bridge, where people got stranded in the middle of October, where it's very cold as well in Austria already, meaning below 0 degrees in some cases as well. And this really led to dramatic situations there. And of course, we all, but especially humanitarian aid organizations, face challenges through these intensified refugee movements. And what our goal is to obviously, let's say, ensure humanitarian safety through a better reception, transfer, supply, and accommodation of refugees. And what we need, and that's the story here again, is integrated situational awareness. Good. Now, what we see here again is what I mentioned before. This is a large-scale situation as compared to before, meaning we see the entire southeastern part of Europe, Austria here, the Balkan countries, Italy, and then the border between Greece and Turkey over here. Good. So now what we can see again is hotspots of refugees, because people on the go, they post and they would say things like, I just passed through the border from Croatia to Slovenia, or we're getting stranded here at wherever it is, and so on, right? And this means that at different times, the spatial focus of these data changes. And if we take a look at this spatial temporal visualization again, we can jump a little bit ahead here. We see that in the beginning, the border between Greece and Turkey is very intense, obviously. The first part. And then all of a sudden, things start to move over, first of all, to the Balkan regions, but then also to the border between Serbia and Hungary, and then Hungary to Austria. And then what's very interesting is you see this border between Serbia and Hungary very strongly frequented. And then Hungary built this infamous fence here between Serbia and Hungary. And then what happens as a consequence is that people would move over here, which is entering Austria through the southern border through Slovenia. So you can basically follow these movements as you see here, follow these movements in somewhat real time. And this is a daily resolution, by the way. and we can go down also further with higher temporal resolutions. Good. The next part is an origin destination analysis. We know where people are, and sometimes they post from where they go to. As I mentioned before, from Croatia into Slovenia. I'm just getting on the train in Budapest to Munich or something like this, right? So there is lots of information in there that we can leverage on the large scale. So everything I'm talking about here, it's hundreds and hundreds of thousands and millions of posts, right? To say that this is something which gives us a large-scale situation that's statistically robust as well. Okay, what you see here on the right side in this chord diagram is that you really have arrows, namely flows from A to B. For example, from Serbia mostly into Croatia, Croatia into Slovenia, Slovenia into Austria mostly as well, but also Hungary a little bit, and so on, right? You see a very clear flow where people come from into Austria is mostly from Hungary, as you see, but also from Slovenia. And that's exactly what was represented before in the map as well, but in a more structured fashion. Yes, of course, we have a large share, which is a third, obviously, of undefined locations. So people just only mention one part of the origin destination pair in their post. So I'm just leaving Hungary, or I'm just going into Austria. So that's there is one information lacking, so to say. But then again, we have a good idea that again people are leaving Hungary to where we don't really know. But then there's a statistical chance that people would go into Austria. And what we saw there is Hungary to Austria was this big highway, Balkans into Austria, especially Slovenia, obviously, and then Austria into Germany as well, which is this green and yellow arrows basically where people would move on, so to say. Good. And now for the last part, I would like to go into our large-scale exercise that we held last year, which basically took place in Salzburg last year again. Good. What did we want to do? Everything I told right now was pretty much scientific. Now what we wanted to do is to test this in real practice. We gathered 900 action forces, which were directed by me, and in 4 disaster areas. 4 disaster areas I'm going to get to in a second. You see some of them here already. Now, the idea was we had a realistic crisis management board. S1 to S5 is basically the functions in a crisis management board, which is judging the situation, which is resource deployment, which is communication, which is PR and media, and all different kinds of things. So they were realistically set there, and the participants were those which also take care of crisis situations in real crisis situations, not like fictitious ones as we had right here, which is the region of Salzburg, which is the Red Cross, which is Johanniter, another rescue organization, a technical rescue organization, THW, and of course the fire brigade. And then we had, let's say, also external people from the military and from the police. And the idea in general was to have a fully digital crisis management center at our Ideas Lab in Salzburg. And digital, you remember the first or second slide I showed where people pinned things to the wall. We really tried to push people into using our digital tools and the information layers that I just showed before. Good. So this is the crisis management room. And these are the real people. So that's the head of the crisis management board for the region of Salzburg. That's the head of the crisis management board for the Red Cross. So these are like real disaster managers who did this exercise with us. And that's all the heads of the regional organizations from the Red Cross, the police, the fire brigade, and the water rescue. Good. The idea was, of course, to evaluate then the usefulness and the usability of these information layers that we produce. Good. The general background was analysis of heterogeneous big data sources, not only social media posts, but also remotely sensed data, then quantify the spatial extent of the affected areas. These were the 4 crisis areas, so to say. In the middle, you see the city of Salzburg. Then you see the Kirchen out here, Oberndorf-Laufen here, and Kuchel here. What happened there? Some of them are larger scale, so that's the entire city of Oberndorf, basically. That's very fine-grained in the city of Salzburg, and it was all within like an area of, I don't know, 50 by 50 kilometers. Good. The general idea that we simulated was that we assumed that there was a very severe storm and rainfall event that caused large-scale flooding in the entire area. Good. Over here, we see the river. So the simulation was that people have been caught by the river while trying to traverse it and needed to be rescued. In Salzburg, a collapsing building. So we used a building that was just like demolished to be rebuilt, as you will see. Then here we simulated flooded houses to really bringing in roofs into a lake, as you will see as well. And then down here, we simulated a derailed train. The train was provided by the Austrian Railway Services, and we assumed it was even a train carrying chemical goods, meaning a CBRN unit was also there for decontamination. It was a complex situation. They were then coordinated from, again, our lab in Salzburg, and it was quite, let's say, high intensity as well. Which information layers did we use? This is what I talked about already. So on the bottom right, on the right here, you see the temporally changing hotspots, first out in the Kirchen, then going to the city of Salzburg, and then moving along over time in space. And then, of course, we also put in images and social media posts that arose from there. Good. Additionally, we had social media reporters, like live reports from the field. Young people from the Red Cross, they were just out on site and posted things on social media. And then we could basically integrate this into the crisis management system in real time, the common operational picture. That's what COP stands for. Then, of course, radar and satellite imagery. So these are permanent water bodies, and these are temporary water bodies that just arose through the flooding here, as you can see in the 4 different areas as well. Then, of course, optical satellite and drone imagery. So we did a drone campaign in these 3 areas here. And what you can see here is that we have a satellite image from a longer time ago, which is 3 years ago. This is the city of Salzburg. This is the building that has been demolished, as I'm going to show in a second. And this is the area where the train derailment was caused. Second, this is a satellite image from right before the exercise. You see that the building has already been demolished, and a few things have changed here as well. And then there is drone imagery as well, right before the day of the exercise. Again, you see the demolished building in very high resolution. And what we did there is to run a building and vehicle detection algorithm. And what you see there in yellow are the buildings, and in blue are the vehicles. Good. And then came the clue, namely information fusion. How do we generate a situational awareness picture that contains all those information pieces? First of all, remotely sensed data. Second, social media hotspots. Third, population at risk, mainly population density. And this gave us an idea in focus maps, so to say, and you see how they change over time as well, right? In focus maps, how we can or where we can deploy the resources and what the most urgent areas are to be helped. Good. This is a 3D model. You see that you can click on things. This is a social media post where you see all the different, let's say, damages and so on. So this was the building I showed before, right? The demolished one that we used for simulating the building collapse. Measurement tools in there, all different kinds of information integrated. Good. Now, this is what it looked like. So here is the demolished building, including dog rescue action. Then this is the train accident. This is the crisis management board. This is the overview, so to say, situation. And this is the rescue from flooded houses, so to say, helicopter rescue. And I'm just going to show you quickly how this works, just a short movie, a few minutes. Don't hear the sound, let me know.
In a large-scale disaster management exercise, the IFA field exercise, the cooperation between science and emergency management operations was tested at 4 locations in the city of Salzburg and surrounding regions, supported through a high-tech operations center. The exercise assumed a severe storm event causing large-scale flooding. Spectacular rescue operations were performed in Seekirchen, the city of Salzburg, Oberndorf and Kuchel. I can summarize that the exercise goal was achieved and that the information, which has been produced by the analysis of artificial intelligence algorithms, can strongly support us in operational management. This exercise is of interest to disaster management operations in 3 ways. Firstly, the analysis of geosocial media data and the use of artificial intelligence in order to be able to identify disaster hotspots even more quickly. In other words, where is something happening at what time? The second point is the provision of live images from drones or helicopters, which can be fed into control centers. And the third aspect is the intersection and interaction between science and research. In this case, geoinformatics research provides information layers that make disaster management more efficient. On the one hand, we use posts from social media, and on the other hand, we use satellite and drone images, which we then combine to generate a comprehensive, common operational picture of the disaster situation. This offers insights that would not have been possible before. The Red Cross, the armed forces, the fire brigade, police and water rescue teams have evaluated the disaster on site in Seekirchen. This real-world exercise has an extraordinary opportunity for us. Being able to work with different organizations from practice and science is extremely important. We are thankful that the exercise was being carried out at Lake Wallersee and that we were actively involved. Of course, the organization of the exercise here on site required significant preparation effort. Now being here, the exercise is going great and we can only draw positive conclusions. For us, it is very important that a wide variety of radio communication practices are tested. The cooperation between different emergency services organizations is incredibly important. Today also showed where we need to improve things a bit. And for us, it was an educational exercise to define our future strategy and practices. Such exercises serve to coordinate cross-border aid even better than before. They also enable us to test new methods in a practical way and under realistic conditions. And above all, they serve to feed the findings back into research, so that in the end we will research what will help our disaster management practices and thus how we can protect even better and save more lives.
Good to see that we basically went to the lab and to the wild, so to say. So this was really much a very intense disaster management exercise, and it was not only, let's say, playing around on the computer, but it was really much a very strong real-world situation that many people, again 900 action forces close to, were involved on site, like cutting people out from cars, helicopter rescues, all different kinds of things. And the crisis management board obviously used our information to coordinate the whole thing. It worked well, I need to say, and that's fortunately also what our interviewees say. So again, the head of the Red Cross and the other person you saw was the head of the regional crisis management infrastructure. Good, so conclude. Why do we think the geosocial media analytics works well? First of all, we see this worldwide availability. We have data from all over the world and we can zoom into regions very much dynamically and it's somewhat real time, and then model the spatial spread of crisis situations in very, let's say, high frequency steps as well. It's then a continuous data stream, right? So real-time situation reports are possible. We continuously get data, we analyze them, we put them out. So it's really much a no wait time, so to say, for us in analyzing the situation. Yes, an initial installation can take up to 6 hours when people call us and say, look, we need data for whatever crisis situation at Typhoon in the Philippines. We just need a little bit to gather the first bunch of information, and then we can produce like updated information layers, I don't know, for example, half hourly, but basically on the go. Yes, intuitive information visualization is always a very big one. So this is a big learning for us as well. People tell us, like crisis managers tell us, look, it's great what you do there with all the complex data sources and machine learning and multimodal analysis, which we don't understand anyway, and we don't have to. But it's too complex for us also in terms of like how usable it is. Right? And what they say is, I only want to have a green or red area. Do I have to interfere there? Do I have to intervene or not? And that's the only thing they want to know. Yes, of course, that's only half the story from my point of view, because it disregards a little bit the complexity of crisis situations. But the problem in crisis situations is obviously that everybody is very much under stress and hectic. So we need to be very simple in visualizations as well. Good. As I showed, transferability between use cases and geographic regions is given. We can zoom into all different kinds of aspects. And we already did a few real-world use cases, about 10 to 15 already, which went from earthquakes to the Armenia-Azerbaijan conflict in Bergkarabakh, the Beirut explosion, the nitrate explosion, if you remember, in 2020, COVID-19, as I showed, then, of course, the Ukraine-Russia conflict, the refugee situation, and all different kinds of let's say, use cases. So it seems to work well for all of those. Yeah, simple integration into of this information to disaster management process. I would say yes, that's possible, meaning we have standardized technical interfaces that everybody can use. So in integrating this information into tools for visualization and crisis management is quite simple, technically speaking. But again, we need to generate decision support information with the users together. So currently, there is still a gap between what we deliver and what people can really use in crisis situations. And that's what we're working on right now. And then there is, of course, the final statement. How do we go from research into practice? There is two things. First of all, how do we use digital information efficiently in disaster management? It's a very, very long process. As I showed before, people are still drawing on walls and so on. Now, how do we get digitalization into the entire process? How I think it can happen is integration into the disaster management process through continuous training. Because if we train how to use this information, I don't know, 4 times a year, and we talk about it, and how can these hotspots be interpreted, and what are the caveats, and what can I see, and what conclusions can I draw from that? If I know this through continuous training, I would obviously be more willing to also use this in a situation that, of course, as I mentioned, is stressful and where cognitive capacities are limited by definition. Good. We also created a training and educational film, which basically is targeted to first responders and how to integrate this information to the process. Good. That's it from my side. Thank you so much for being here. Thanks a lot for the invitation as well. It's absolutely much a pleasure. And I also wrote into the chat, like, if you want to ask your questions, please do let me know. And of course, please feel free to contact me. You find my email address at the ITU website. It's basically berndresch@itu.at. Thank you very much.
So if you have any questions, please raise your voice.
So just to say that at the moment we have quite some positions open. Alone in my research group is like 8 positions that we're looking to fill. So please feel free to let me know if you're looking for a collaboration there.
Okay, if there are no questions, thank you so much for your excellent presentation. There is a question.
Yes.
On the chat.
Can you talk about data collection in multimodal? Yeah. So for us, the multimodality comes from the inherent multimodal nature of social media data. So when we download a social media post, we get, I don't know, about 20 or so attributes, right? Which is geolocation, which is time, which is text, which is images and media, which is a few user characteristics, including their home location and so on. So this all gives us the opportunity to better analyze and understand the crisis situation. Now, how we do this, it's basically a very simple process. Everybody who can program a little bit can use an API. You connect to the API and you get the post that you wanna have. How exactly do we do it? For us, it's mostly a spatial search. So we say, please, dear API, I have a point here. Please give me all posts in an area around this point. And then a number of posts will come back, and we do this repeatedly. And like this, we build up our data set. So we do the semantic filtering only afterwards. And that's for the reason because we need to normalize over population density to some degree, or at least we need to detect anomalies. Mostly normalization, by the way, happens through normalizing over the usual number of posts. We have a baseline, like every day so many posts are flowing in, and now there is something different. A new topic pops up. A significantly higher number of social media posts and so on is being sent. Basic idea, I'm just going to post my email address into the chat as well. How do you efficiently label unlabeled data? That's a very good question. Oh, sorry. There was another one, verbal one. I'm going to get to that in a second.
Hi. Okay, there's another question on the chat, or should I ask mine? I think
Please
there is
ask
another question.
Then I'm going to get back to Anin.
Okay. So just a quick thought about the part of the presentation where you were talking about clustering. Where you basically spoke about how different tweets or other social media content is clustered.
Yeah.
So my question is that when you compute the distance, is it always considered a Euclidean space in the sense that you are basically using the Euclidean distance formula for a flat space? Or is it also something that has been explored in non-Euclidean spaces?
Yes, I mean, that's a very good question. And I mean, as we are geoinformatics people, half our work and thoughts revolve around projected versus geographic coordinate reference systems. So this depends very strongly on the nature of the disaster, meaning how large the area is. If we have very small areas, we can somewhat safely assume that we can use Euclidean distances, but otherwise we have to go for different distances, which is, for example, the Haversine distance, which goes in distances on an ellipsoid, basically, right? But there are, let's say, these are really standard
sorry.
methods.
Yeah, sorry, I think I wasn't clear. I wasn't talking about the geographic distance. I was talking about the distance in the feature space.
I see.
Yeah, so basically the clustering, exactly. So the clustering in the n-dimensional feature space, as I understand from literature, it is almost always assumed that it's a Euclidean space.
It is assumed that it's
so you basically just use the distance formula for a straight line. I think there was the slide with the way you showed the network. Yeah, exactly that one.
Yeah. So yes, in this case, we do assume Euclidean space, and the problem here is lacking understanding of the phenomenon. How would you define, or why would you define a different type of space? Because you need to have an understanding of how a phenomenon, in this case, the connection between social media posts in the context of crisis management, is actually set up, like what the transfer function, so to say, is, right? And for us, that's intransparent. We just don't know, frankly, and that's why we assume Euclidean space for now. But if you have any suggestions here, more than happy to follow now.
Yeah, actually, just I was actually mostly curious because I mean, I understand if you go out of Euclidean space, then the question is that which kind of non-Euclidean space are you considering and why you're considering that?
Always.
And if there is, for example, any metric of sort that you could consider in judging, for example, if you choose a certain kind of non-Euclidean space, is it possible to judge the performance of the overall, so to say, the use case?
Yes, so that's very hard to say, obviously. So for the unimodal use case, that's quite straightforward because we just built a confusion matrix, and data labeling, which is the question that Anine asked, is rather straightforward, right? If we say we have, I don't know, a pixel that is labeled as flood, and we go out and see it's flood, okay, that's a ground reference, a ground truth to some degree, right? Whereas in other use cases, it's harder. So first of all, like sentiments and emotions are very much subjective, and there is no ground reference. We can just assume that it's correct, and we can find an inter-annotator agreement there. So it's intersubjectively correct, but there is no objective reference there. And then makes things very, very tricky. So we have a number of quality metrics which are mostly relating to plausibility rather than correctness.
Okay, I understand. I see what you mean. Okay, great. Thank you so much.
And very happy to follow up because that's a very, very good question. Same with the one from Anine now as well. For the labeling, it actually ties in with each other. So efficiently label unlabeled data. There is a question what we mean here. Let's say for semantic topic modeling, it's rather easy, I would say. Semantic topic modeling is not too hard. Like people talk about a certain topic, and there are different topics, and then the topics contain a number of words and documents, and you can rather easily figure out what people are talking about. This you can do manually, or you can even do, as I mentioned, using a generative semantic model like Llama or whatever it is. For training a supervised, let's say, model is way harder, obviously. Let's talk about emotions for a second. Emotions are a very tricky thing. Emotions are an emotion psychological process, not a cognitive process, obviously, right? And so meaning what people feel, what they really feel, and what they report they feel may not be the same at all. And that's a challenge. Second, how you express emotion semantically in words is still a very, very big gap. There are virtually, let's say, infinite ways of doing that. Now, picking that out is hard. And then, of course, in the labeling process, trying to identify which emotion another person felt is really hard. So to answer your question concretely, our current approach is consensus-based labeling. Because what does not work, definitely in sentiment and emotional analysis, is that you just give people a number of posts and they just start labeling. You have a small labeling guide and you just label. It does not work, not at all. You get a very bad data set. Now we have a labeling guide that is very long, very extensive, and very detailed to tell people what to do and what not to do, and what to interpret and what not to interpret. And second, we really follow a consensus-based labeling approach where usually 3 of us sit in a room, or 3 people sit in a room. And then we, in case of disagreement, discuss which emotions could be in there. And of course, a minority vote is always possible. Like one person says happiness, one person says joy, says fear, and one person says anger. That's always possible. But at least through a discussion, you get to a same level of understanding how to interpret the emotion, even though it's not labeled the same. Good. So the follow-up question from Yonin, do you think your approach can be used to identify the source and or points where the disaster, a flood, is coming from and how the info is diffused to affect places? Yes, definitely. So when we talk about, yes, I'm going to be short, Philippos. When we talk about flood, like floods are very well researched, right? When you say it rains up there and it rains in the mountains, and hydrologically speaking, the water is accumulating and then it's progressing throughout space, like down the river. That's rather easy to predict. What's very hard to analyze is flash floods. And flash floods, like earthquakes, for example, cannot really be predicted because you do not really know why they actually happen and what the thresholds are, so to say, that these flash floods actually happen. So yes, spatial diffusion and propagation is one of our central research areas as well in terms of prediction where a flood location, so to say, will be in the near future. Thanks, Philippus, for pointing that out. And Anina,